They're calling you, Susie. Go get your dinner. Okay, 8.4 is what we have to go over today. And so we're going to be looking at that. We'd already seen this rule here in 8.2 and also in 8.3. And now they're going to have us use it the opposite direction. So they had us breaking it apart and then taking the square root of the pieces. So we had done that. And now they're going to have us put it together. So here they're telling us that to multiply and simplify, and all variables are non-negative. So you don't have to worry about absolute value, is what they're telling us. And I was telling people that they only worry about absolute value for a very, very short time there in 8.2 because they only, the rest of the time they say non-negative. So this is the square root of 6 times the square root of 5, according to this property right here, that this is the square root of 6 times 5, which is the same as the square root of 30. Now you should simplify that, but 30 won't simplify because 30 is, if you prime factor it, is 2 times 15, which is 3 times 5, right? And so you don't 2 times 3 times 5, you don't have any of these factors repeated twice. And so this is it. So there is no perfect square that divides evenly other than 1 into 30. Then here, this next example, they're having us to multiply this together with this. And how you multiply those together is you multiply the numbers that are the coefficients, the 3 and the 2 together. And you multiply the things that are underneath the square root together, 5a to the 7th times 15a to the 3rd. So, and this is your thought. And most people don't even write that. And so you're going to get 6 here, and you're going to get the square root of 5 times 15. Is that 75? I think 5 times 15 is 75. I'll check it just to be on the safe side. It is a to the 10th, right? Unlike square root of 30 over here, the square root of 75 does have a perfect square that divides evenly into 75. And so it's 25, right? And so if I wanted to do the prime factoring method of simplifying the square root, I definitely could. 75. Or I can do know the perfect square method, it doesn't matter, is 3 times 25, which is 5 times 5, right? So this is 6 times the square root of 3 times 5 times 5. And the square root of a to the 10th is actually, a to the 10th is a perfect square because I'm asking you, if you were to write this all out, AAA, right? AAA, 10 of them, how many groups of 2 could you circle those in? If you have 10 of them, it's 5 groups of 2, right? And we talked about the fact that that is just division, 10 divided by the index, which is 2, which is 5. So anyway, when we take the square root of 25, we get 5. So we had a 6 outside already, and we get a 5 out. And then when we take the square root of all of these a's, we're going to get a to the 5th, and then stuck underneath is the 3. And so this is 30a to the 5th at square root of 3. And then that's it. So we did a lovely job on that. So they're having us practice some multiplying. It also has simplifying that we learned in there. And so we're going to continue on. Here, I didn't have to worry about absolute value because non-negative, right? And so I would have had to worry about absolute value had it not had that it was non-negative. So here, the variables are non-negative, so I don't have to worry about absolute value. When I multiply these together, right here, 6, the square root of x times 6, I have to do the distributive property. Those won't multiply together. And so the order that you write them in, though, is the number first and your square root second. So this is going to be 6 square roots of x. And then this is the square root of x times the square root of x. So this is minus the square root of x times x. So they're both square roots. And for every 2 that are the same, right, 1 comes out. And the way I've written it is really nice there. You could have also written x squared. It would be the same. So this is 6 square roots of x minus x. And that's okay. You can write it just like that if you like. In the back of the book, they might write their square root second. So they might write minus x plus 6 square roots of x like that. And that's also good. So or. You can choose it. So we did a lovely job on that. And I didn't need absolute value because they said non-negative on the variables. So here, this one doesn't have any variables in it, and it's got the cube root of 2 times the cube root of 4 here. And so if you wanted to do the multiplying first, you could. If you wanted to simplify, the cube root of 4 doesn't simplify. But the cube root of 32 does simplify because 32 is 2 times 2 times 2 times 2 times 2. It's 2 to the 5th, right? And so there are 3 2's underneath that cube root. So your choice on do you simplify that right now or do you multiply? And it'll give you the same answer whichever one you do. And so I was thinking, I was looking at it and I was noticing that, hey, if I multiplied, this is the cube root of 8. 2 times 4 is 8. I think I'm going to write that, my thought here. So this is 2 times 4 underneath that cube root. And then here, minus 2. And there's nothing to multiply with the coefficient 2 other than a 1 that's here, right? And 1 times 2 is 2. And then underneath the cube root, we're going to be multiplying 2 times 32. And I just wrote that so that you know that's what I was thinking. And so this is the cube root of 8, and I think that's what most people would have written first, because they would have said, oh, it's 2 times 4, that's 8. And the cube root of 64. And the cube root of 8 is a perfect cube. That's 2. And the cube root of 64 is also a perfect cube. And so this is 2 times, and the cube root of 64 is 4. And so this is 2 minus 8, which is negative 6. I almost wrote negative 4. I did write it, and then I fixed it. I don't know. I'm always on you guys on your neatness. So maybe I'll be a little neater there and do a little erasing. I had an eraser here, but my eraser keeps getting lost. Okay, so next page. So more multiplying. They're asking us to do multiply and simplify. And I'm going to do FOIL, right? So this is a binomial times a binomial. You might notice that, hey, when you multiply that together, the way that's set up, the outer and the inner, do you guys remember that sometimes the outer and the inner make 0, and that's exactly what's going to happen on this one here. So if you wanted to notice that, you could not multiply them together. If you wanted to multiply it together just to make sure that they go away, you could. So we'll give a try to it. So this would be the square root of 12 times the square root of 12. So that's the square root of 12 times 12. This is minus the square root of 12 times 5. And in here is plus the square root of 5 times 12. And last but not least, minus the square root of 5 times 5. And then 12 times 12 is 144, and the square root of 144 is 12. Well, for every 2 that are the same, 1 comes out, so I could have done that. And this is minus the square root of 60. This is plus the square root of 60. And then this is the square root of 25, which is 5. Or for every 2 that are the same, 1 comes out. So this is minus 5. Long story short, these are 0, just like we said was going to happen with the outer and the inner. And I'm going to get 12 take away 5, which is 7. And so kind of unusual that I would multiply something so ugly looking together and just get 7. And they're going to tell us that those have a special name that go with one another. So this one and this one, when you put them together, have a special name. And then it's coming. And so now they're asking me to square this right here. 4 plus the square root of x minus 3 squared. And so remember that when you square a binomial, that's what this is. This is the first term, and here is the second term. The square root of this whole thing is the second term. And so when you square a binomial, you write it twice and do FOIL. Now when you do FOIL with things that are exactly the same, whereas these had the plus and the minus, right? You don't get the outer and the inner dropping out. You're going to get actually double your outer and your inner, right? And so I'll just multiply it and see what I get. So 4 times 4 is 16. And here I'm going to get plus, and you can't multiply those physically together. One's a square root and the other's not. So you just write the number first and the square root second. And when you do the inner, same thing. Write the 4 first and the square root second. And then last but not least here, that's going to be, it's a plus. Oop, and I didn't get a plus written very well. And so, so there's my plus, and then I'm having the square root, and this is x minus 3 times x minus 3. See how they're both the same there. So here I'm having 16. Here, these are like terms. And so they're both square root of x minus 3. So you could just add the coefficients together. 4 plus 4 is 8. So 8 square root of x minus 3. And then this is tricky. We've seen this a couple of times though, right? These are exactly the same, and for every two that are the same under a square root, one comes out. So you're going to get plus x minus 3. Right, so there's 2 of them. Some people say, you know, when they had algebra before, their teacher went the extra step and wrote x minus 3 quantity squared, and then told them that, hey, the square and the square root undo one another, and hey, that's good too, right? Sounds good. And then when I look in the back of the book, they're definitely going to combine like terms because they asked me to simplify. So 16 take away 3, they're definitely going to call that 13. But as far as the order after that goes, they may or may not write the x first, the 13 second, and the square root last. And so that's kind of the descending order that I was taught. And the book, the back of the book, both of these are good, right? Just preference. And so anyway, so we did a lovely job on that. Okay. Then the same story that we were just doing with multiplication with division. And so we're going to give a try to that. So we had used this property yesterday as well. And so they're just having us now, actually we had done it both ways, 8.2 I think. And so here, the idea is, the thought is that, so this is my thought, is I'm going to do 4 divided by 2, and I'm also going to do the square root of 35 divided by the square root of 7. And this can be in 1 square root, so I can write this under 1 square root. So this becomes 2, 4 divided by 2 is 2, and the square root of 5. And that's a funky looking 5. I was looking at the monitor, so I was watching myself write, and it got funky because of that. I almost made myself dizzy. Okay, so we did a lovely job on that. So same thing here is that the things that can reduce to one another are the 3 and the 12, and the cube roots can reduce with one another. The x there doesn't have anyone to reduce with, and so this x right here doesn't have anyone to reduce with. So on our initial reducing. So if we wanted to kind of start looking at what's going to happen, so when I do 3 in the 12x, or the 12, you're going to get a 4 in the denominator. And so when you reduce these right here, right, you're going to get, you can put a 1 in the numerator if you want, and then a 4x in the denominator. The x had no one to reduce with, and 3 and 12 reduced to be 1/4. And then in my thought, I'm thinking, you have the cube root of 16x squared y, cube root, of both of these. And this is 2y, right? They're both cube roots. So I'm thinking of this. When I reduce that, I'm going to get 8x squared, and the y's are going to reduce. So it's the cube root of 8x squared. And where that would be is in the numerator. The denominator, the 2 and the y, they reduced out, right? And so up here, times, and then the cube root of 8x squared. Now, the cube root of 8 is a nice friend, right? The cube root of 8 is 2. You could prime factor it if you wanted. 2 times 2 times 2, right? And times x, but there's not enough x's for the x's to reduce with one another. So this is going to be the 1. I don't have to write it anymore. So I'm going to have 2, because I'm taking the cube root of 8, and then stuck underneath the cube root will be x squared, and then in the denominator was 4x. And actually I can do a little more reducing now, because the things that would reduce is the 2 and the 4 could reduce with one another. So in the numerator I would be left with the cube root of 2x squared over the 4 and the 2. When they reduce, they give a 2x. Now this x cannot reduce with that because they're not both underneath the cube root. And so the x still doesn't have anyone to reduce with. And so there we are, all done. Hot diggity dog, you say. So, and so these square roots are new, and all the reducing them and whatnot is, I know, it takes a lot of practice to do. So just a reminder on how to get things simplified. They'd already told us this, but the only thing they made us work on was number 1. So in 8.2, they told us about how to simplify radicals, and the only thing that they gave us to work on in 8.2 was number 1. And so I'm telling you, reminding you, because now they're going to make us work on number 2. Number 2 is there are no fractions under the radical sign. So right here, we have a radical sign and I have a fraction underneath it, and that's not considered simplified. So one of the things that you can do is you can apply what they were just telling us, which is the square root of a divided by b is equal to the square root of a divided by the square root of b. So we had been doing that, and so you could apply that when you have a fraction. So in this case, that would be the square root of 7 over the square root of 2. So it wasn't simplified because I had the 7/2 underneath the square root. And now the problem is number 3. It's not simplified now because it says no radicals. Now the square root symbol is a radical. Also the cube root symbol is a radical. No radicals in the denominator. And so I have a radical in the denominator. And so that's not simplified. So I want to get rid of that radical in the denominator. And so how I'm going to get rid of it is make the square root of 2 into a perfect square. So if I multiplied the square root of 2 by the square root of 2. So the reason I'm doing that is I want to get rid of the radical in the denominator, and look what this becomes. It becomes the square root of 4, which is 2. And see how I trickily got rid of the radical in the denominator. Now you're not just allowed to go multiply a denominator by the square root of 2. You can't do that. Whenever you have a fraction, you can multiply by 1. And so that would be the square root of 2 divided by square root of 2. This is equal to 1. And so that means that when I multiply this fraction by 1, it might look different, but it has the same value. They both have exactly the same value. And so when I multiply the top here, square root of 7 times the square root of 2, that's the square root of 14. And the square root of 14 can't be simplified because 14 is 2 times 7. So this is the square root of 14 over 2 as our answer there. I'm going to write that out here where you can really see it. square root of 14 over 2. And that can't be reduced because the square root, the 2 is not underneath a square root. So even though you might be thinking 14 divides by 2, well, this is not 2. That's the square root of 2. 2 times 7, right? Square root of 2 times 7. So it's not, it doesn't have a 2 as the factor of 14 because it's underneath a square root. So it's a square root of 2, and that will not reduce with 2. The square root of 2, you can ask your calculator what the square root of 2 is if you wanted, just to know. And the square root of 2 is around 1.41421356. It goes on and on and on. We talked about those earlier, about them being called irrational numbers. It was way earlier, chapter 0 or chapter 1. It was a long time ago. Anyway, so the vocabulary that goes with this situation, the square root of 14 is an irrational number, is to rationalize the denominator. And so that's what they're asking us to do. And the square root of 2 is an irrational number. And so there is an irrational number in the denominator, and they want us to turn it into a rational number. That's what rationalize means. And 2 is a rational number. And so that's what we've done, is we've converted the irrational number, square root of 2, into the number 2. There's quite a few historical reasons for why people rationalize the denominator by multiplying by the special 1, like we just did. And one of them is just ease of division. And so people would look up, people didn't have calculators, and they would look up what the square root of 7 is and divide it by the square root, if they wanted to divide it by the square root of 2. And the square root of 7, you would actually look it up in a book, believe it or not. And the square root of 7, so the square root of 7 over the square root of 2, just to show you, is 2.64, and it goes on. And remember that square root of 2 was 1.414. And think about long dividing that. And that would be difficult. And particularly if I wanted to take it 9 places or whatever have you. But if you rationalize the denominator, you would just have to look up the square root of 14 in your book, which is, so the square root of 14 over 2, which is 3.74165, however many places you want over 2. And then that's really easy to long divide, 3.74165. No moving the decimal point as you write it as in the division or anything. You know, 2 goes into 3 one time, and remainder 1. So you get 17. 2 goes into 17, 8 times 16, and on you go. And so it's really, so that's a historical reason why rationalizing the denominator was really important. When you get into STEM classes like pre-calc and calculus, you're going to see more use of rationalizing the denominator, and also actually rationalizing the numerator. There's times that you want to make the numerator a rational number. Right now, my numerator is an irrational number, and my denominator is a rational number, and that's what they asked me to do here. So anyway, and so you're going to get there. It's coming. Okay, so this one, they're wanting me to rationalize the denominator. So no radicals in the denominator. That's number 3. Not allowed to have a radical in the denominator. And I want to make a perfect cube underneath the cube root symbol. And so I don't want to make a perfect square because it's a cube root, right? I want to make a perfect cube. And remember, when you have a cube root, it takes 3 of each item for 1 to come out. So I have 1 3, and so what I'm going to need in order to make a perfect cube root is I'm going to need 2 more 3s to make 3 3s altogether. And what I've now just created there is the cube root of 27, and that's a perfect cube. Now I'm going to have to work on my x's, my y's as well. I have 2 y's, and to make a perfect cube root, I need 3 y's. So I already have 2, so I need 1 more. So when I put one more here, then I'm going to have over here, when I multiply them together, y to the second times y will be y to the third. And I've created in the denominator something that is a perfect cubed by building it, right? And I build it with the knowledge that it takes 3 of each factor to be a perfect cube. So I had 1 3, so I needed 2 more to make 3 3s. I had 2 y's, so I needed 1 more to make 3 y's. And what you do to the top, you got to do to the bottom. And what you do to the bottom, you got to do to the top. So I've multiplied by the cube root of 3 times 3, which is 9, times y. And I'm going to have to do that to the numerator. And I'm not caring what happens in the numerator. What I'm caring about is what happens to the denominator. I want there to be no radical, no cube root. And so in the denominator, I actually, when I multiply this together, 7 times 9 is 63. So this is the cube root of 63xy, right? When I multiply those two things together, 7 times 9 is 63xy. And the numerator, I'm not going to be able to do anything with it. So if you prime factored it, here it is, it's prime factoring. There's no repeated roots that are 3 of each factor. But the denominator, this is a perfect cube. I made it so. This is 3. This is a perfect cube. I made it so, y. So this is 3y over the square root, the cube root, rather, of 63xy. And no, you cannot reduce the 3 and the 63, and no, you cannot reduce the y's. This is underneath a cube root, and this is not, so you can't reduce them. And so that's it. And so all they asked me to do is get rid of the radical symbol in the denominator, and I did by multiplying by the special 1. So there's the special 1 right there. And I built it by saying I need 3 of each. Okay, so this is number 56, 3x divided by the square root of 20. And you have choices of what you would do. My first thing would be to say, well, I don't want it to be the radical of a fraction, and I would write it as the square root, this one's the square root of 3x divided by the square root of 20. And then the square root of 3x doesn't reduce, but the square root of 20 can reduce because 20 is 2 times 2 times 5. And so my choice, if I want to reduce that first, and I think I'm going to. So so if you're saying, hey, I have another idea of what we can do, I'm saying to you, wonderful. Try your way and see if you get the same answer. You should. So, so there's more than one way of going. So here I'm thinking that's 4 times 5 is 20, and the square root of 4 is 2. And so this is the square root of 3x over 2 times the square root of 5. And I would be all done except for you're not allowed to have any radicals in the denominator. And I have the square root of 5 in the denominator. There's nothing wrong with 2. 2 is rational, right? And so, but I need to get rid of the square root of 5. And so I'm going to multiply it by the special 1. Now remember, I want to turn this radical into a perfect square. And so I'm going to multiply by the square root of 5 to do that, top and bottom. So in the numerator, I get the square root of 15x. It is what it is. And in the denominator, right, I get 2 times the square root of 25. I'm going to take every step. So if you're like, I had an idea of how I could have skipped a step there, I'm going to write every step. And then that is the square root of 15x over 2 times 5, because the square root of 25 is 5. So if you said that, hey, this is 5, and I'm just going to go right to it, that would have been great. And then this is 10. And no, it does not reduce. The 15 is underneath the square root and will not reduce with a 10 that is not underneath the square root. And I want to make sure that you know that my square root includes my x there. So I'm really making my symbol. So we did a lovely job at that. And so here we are working along on 8.4 out of our textbook. And yeah, there's quite a bit more on 8.4. It just keeps going. It's only one more page worth, though. 4 more problems, but it's a lot when we're working so hard. Okay, so they say simplify, assume all variables represent positive numbers. And I look at that and I think, well, 27 and 7 won't reduce with one another. And so the problem is, there's 2 problems here actually, that I have the square root of a fraction that's not allowed. And 7y here, right? So if I wrote it like that, splitting it apart, now I have a radical in the denominator, and that's not allowed. And so what I'm going to do is I'm going to get rid of that radical in the denominator by turning it into a perfect square. And so, because it's a square root. In the numerator, you might notice that 27, that's 3 times 3 times 3, will reduce underneath the square root. For every 2 that are the same, one comes out. And same with the x's, x, 5 of them, right? You can reduce that too. So whether you choose to reduce the numerator first because you have perfect squares underneath the radical, or if you choose to reduce the denominator because you have the square root in the denominator, that is your choice. And so whichever one makes you the happiest to reduce first, I'm going to reduce the numerator. So this is 3, 3, 3, x. If you already know what the answer is to that and you don't have to think this, then more power to you, buddy. That sounds good, right? And so I'm going to get on the outside a 3. I'm going to get on the outside an x and an x, which is x squared. And this is going to be stuck underneath 3x. And in the denominator, I have the square root of 7y. And I'm supposed to rationalize the denominator. They're asking me to simplify. So now I'm going to multiply by that special 1. I want to turn 7 into a perfect square. And how you do that is by multiplying by 7, because 7 times 7 is 49. And I want to turn y into a perfect square. And how you do that is by multiplying by y. Since it's a square root, I need 2 of each of them. So I have 2 of each of them now. And what you do to the bottom, you got to do to the top. So when the dust clears here, I'm going to have 3x squared times the square root. When I multiply these together, I get 21xy. And in the denominator, do you guys agree that when I multiply those together, I would be getting 49y squared, the square root of 49y squared, which is 7y, right? And so I'm going to take the shortcut there instead of writing it as 49y squared. I don't have to worry about absolute value because, again, the variables are positive. They're telling me. I'm going to have to leave this video here and do the last 3 problems in the next video.